All right, so now that we understand a little bit about the basics behind differential equations, we want to talk a little bit more information about them. We're going to talk about something called initial value problems. When we usually solve differential equations, we have set up our model for our differential equation, and usually we have some initial information we know. We know the velocity at a certain time. We know the height at a certain time. We know the amount of substance at a certain time. And so these are all things that we normally can figure out. And so we can solve these initial value problems. An initial value problem is you've got a derivative of y, the nth derivative of y with respect to x is equal to some function of your independent variable x, your dependent variable y, and all the derivatives of y up to the n minus first derivative. And why these are called initial value problem is that we are told we're subjecting them to knowing some values. We know at a certain x0 value, we'll call it our initial value, the y value at x0 is y0. And then y prime is also found at that same x0. That's what makes an initial value, is you're always using that same x0 value. And so you get y prime at x0 is equal to some different value of y, we'll call it y1. And you keep going up, so you get n minus first derivative of y at that same x0 value is equal to some other y value. Notice this is an n degree differential equation, and there are actually n initial values. This y of x0 is your first one, and then there's n minus 1 of the rest. So that gives you n of them. So let's go ahead and do an example. Let's say we happen to know that y prime equals y, and we know the solution of that is y equals c e to the x. Right now, we're not going to show you how we find that solution. We'll be doing that later and then putting this initial value problem with it. And then you're told, again, your initial value problem would actually be giving you that initial differential equation of y prime equals y, and then telling you that y of 0 equals 5. So we want to solve this. So normally, again, what you do is first find out what that derivative, that solution is, but we already know what the solution is. It's y equals c e to the x. So y equals c. Sorry, sometimes my computer doesn't work very well. So y equals c e to the x. I know that when x is 0, we're going to get 5. So that means that c equals 5, because e to the 0, of course, is 1. So now the only thing left to do is write, well, y is actually equal to 5 e to the x. This is a particular solution for this general solution. So y equals c to the x is the general solution because it has the constant, it has an arbitrary constant in there. And the particular solution is we know what that constant is equal to. Let's try another example. Let's try to find the derivative of y with respect to x of y of x times y squared. So the derivative of y with respect to x is equal to x times y squared, and y of 0 equals 4. So I want to solve this differential equation. I happen to, again, I'm not going to show you how we do that, but we will later. We'll figure out how to do these later. So we know what the solution is. The solution is y equals -1 over 1/2 x squared plus c. And now we can go ahead and use the idea that y of 0 equals 4. So that means that if I put 0 in there for x, I get 4. So that gives me -1 over c equals 4. So that means that c is equal to -1/4. So that's again what my constant is, but I actually want to know what the solution is. So the solution is actually y equals -1 over 1/2 x squared minus 1/4. If you don't like all those fractions, you could go ahead and do what you need to get rid of those fractions and see what that is. Just for the fun of it, let's go ahead and find out what the I is. What my interval of definition here. And so we want to go ahead and find that. And again, we're going to look at we're going to look at the domain of this function. The domain of this function can't have 0 in the denominator, so 1/2 x squared minus 1/4 has to equal 0. So what I might do is multiply through by 4. So that gives me 2x squared minus 1 equals 0. So therefore, x is equal to plus or minus 1 over the square root of 2. All right, and then remember your domain, your interval of existence, I should say, is from negative infinity up to that negative 1 over the square root of 2. That's one of them. You could also have the one that is negative 1 over the square root of 2 to 1 over the square root of 2. You could also have 1 over the square root of 2 to infinity. And I put unions in there, and I should not have, because this is not a union thing. These are i's. So it could be one or the other or the other. There's 3 of them here. So we're going to put ors in between. Because I is not all 3 of these. I is one of these many. And in this case, with my initial value problem, I noticed my initial value told me that when x is 0, y is 4. So that means x is 0. So in this case, for my IVP, for my initial value problem, the I is actually the one that contains 0. So the I is the negative the square root of 1 over the square root of 2 to the 1 over the square root of 2, because that one contains that 0. Let's try another example. Let's say c is equal to c1 e to the x plus c2 e to the negative x. This is a solution to y double prime minus y equals 0. Notice this is a second order differential equation because it's y double prime. Notice there are 2 constants, c1 and c2, in my solution. In this case, whenever you have a second order differential equation, notice I have y of 1 equals 0 and y prime of 1 equals e. So we actually have 2 initial conditions. We have a y and a y prime. And if you have a second order differential equation, that's what you will always need. You'll need the y and the y prime. If you had a third order differential equation, you need the y prime, and the y double prime. So again, this is using this equation, the solution, y is equal to c1 e to the x plus c2 e to the negative x. Y of 1 is c1 e to the 1 plus c2 e to the negative 1, and that will equal 0. Well, that's great, but the next one is y prime of 1. Well, that means I need to find the derivative. So my next thing I have to do is find out what is the derivative of y. And the derivative of y is, of course, c1 e to the x minus c2 e to the negative x. And so I'll go ahead and find out what y prime of 1 is. That's c1 e to the 1 minus c2 e to the negative 1, and that equals e. All right. So then I now notice I have 2 equations and 2 unknowns. So this is just a system of equations I can solve. You can solve it any way you want. If you want to use substitution, you want to use elimination, you want to use your calculator, whatever way you want to do. I notice if I add these 2 equations together, I get 2c1e is equal to e. And these 2 terms cancel out. So that tells me that c1 is equal to 1/2. If you solve this for substitution, you'd get a very equivalent c1, but you might have to do a little bit of work to it to get to this answer. Now that I know that, I can use either equation. It doesn't matter which one you use. I'll use the first one, 1/2 e plus c2 e to the negative 1 equals 0. I use this one because it equals 0, and it just seemed like it was easier that way. So c2 e to the negative 1 is equal to negative 1/2 e. Divide through by e to the negative 1, that will give me c2 is equal to negative 1/2 e squared. All right, so again, I will then rewrite my equation. My equation is y is equal to 1/2 e to the x minus 1/2 e squared e to the negative x. So that's actually my particular solution for this initial value problem. The last concept I just want to talk about is the existence of a unique solution. When I did this equation up here and did this solution, I got one solution. I knew I was going to get one solution. I have this one solution right here. That's what that is. In fact, in all of these, I gave one solution. And what I want to know is, how do we know that there is only going to be one solution? And what would that one solution be? So this theorem actually is called the existence of unique solutions. It says let R be a rectangular region defined by the points x, y, where x is between A and B, and y is between C and D, and it contains your x0, y0. So the main thing is if your function, so remember we have a differential equation, y is equal to f, the derivative of y is equal to f, then that f is your function of x and y. And if that's continuous, and what we call the partial derivative of f with respect to y are continuous on R, then the interval I centered at x0, and it has a unique function y of x defined on I. That is the solution to the initial value problem. So going back to this one where we did find I, notice my initial value. I said that I was negative 1 over the square root of 2 to 1 over the square root of 2. My initial value was 0, right? And notice it is centered on that 0. So my I is centered on that 0. It's right there. It's centered there. And that gives me that information. We're going to talk about what this partial derivative means. For those of you who've not had Calc 3, we'll talk about what that means here. Those of you who've had Calc 3, you know what that means. And we have this, you'd have this unique function. So let's take an example of this. I want to determine a region of the xy plane for which the derivative of y with respect to x is equal to the square root of xy has a unique solution. So again, what our differential equations we have to remember is the derivative of y with respect to x is some function of x and y. So that means it is the square root of xy. So my function of xy is the square root of xy. And now let's think about, when is this continuous? Well, this is continuous when x times y is greater than or equal to 0. Because remember, you can't take the square root of a negative number. So as long as it's greater than or equal to 0, you're good. So this is continuous whenever x times y is greater than or equal to 0. Okay, well, that's cool. Doesn't exactly help me very much. It could be when x is greater than or equal to 0 and y is greater than or equal to 0. Or it could be when x is less than or equal to 0 and y is less than or equal to 0. Because remember, two negatives multiplied together give you a positive. All right, so we have that information, but now we're going to talk about this partial derivative. So first off, my function is, I don't like square roots, so I usually write them as x times y to the 1/2. A partial derivative means I'm taking the derivative of this function with just respect to that y variable. So just y is my variable. I'm pretending x is a constant for a moment. So when we go to find the derivative of this, of course, we take the derivative of the outside. So bring the power down, subtract 1 from the power, and then we take the derivative of the inside. But the derivative of the inside is x times y, and y is my variable. So x is kind of like just a function. It's kind of like if you had 2x there, the derivative would be 2. So if I have x times y, if you have 2y there, the derivative would be 2. We have an x times y, so the derivative is just x. All right. So now we're going to find out when that is. Well, that is continuous when x times y is greater than 0. Because not equal to, because this now has a negative exponent, so it's now in the denominator, so it can't be 0. And so this is when x is greater than 0 and y is greater than 0. or when x is less than 0 and y is less than 0. So we now can say that we are going to have continuous on these where these two combine. So my R is a set of all x and y values such that, that's what that vertical line means, is such that x is greater than 0 and y is greater than 0. That's one R. You can also have the R where both are negative, where x, y, and x is less than 0 and y is less than 0. Normally we don't use this one very often because usually our x's and y's, at least our x's are positive. So really our R would be the positive one. And that's kind of what initial value problems are. You know you're going to have a unique solution as long as you pick an x that's bigger than 0 and a y that's bigger than 0 when you do your initial value problem here. And there you have your information.